quote-unquote scaling dimension. So let me give you an example of that. So that's why it's called hyperscaling. So by the way, if you look up scaling theory or critical theory on Wikipedia, you see there are you get a bunch of exponents. You know, the specific heat goes like temperature to some power. The entropy goes like temperature to some power. There are various exponents, alpha, beta, gamma, and so on, nu. And these are all related by something that are called scaling relations. Okay, and these scaling relations are always true. Okay? But there's another relation, it's called the hyperscaling relation. Okay? And that's the one that this violates. So it's not scaling violation, it's a hyperscaling violation. So the hyperscaling is a stronger relationship, and it's related to the scaling dimension of T mu nu. Okay, so certainly in a Lorentzian theory, T mu nu has scaling dimension d plus 1, where d is the number of space dimensions. But what happens is that T mu nu gets an anomalous dimension. Okay, that can happen in this non-relativistic setup. Okay. Yes.
So T mu nu is a certain quantity.
Correct.
So if you integrate it over.
Right. Let me see how does this work. I think that's not enough to fix the dimension actually. Then I'll give you an example now of why this works. So for example, another way of saying it is that basically one way of thinking about it is that, for example, the energy. Let's get this right. So let's think about the free energy. Okay, so basically what happens is that there's some UV scale that doesn't decouple. So I'll write, let's do e.g. a Fermi liquid. So you see, remember that in a Fermi liquid you had this surface in momentum space, and the low energy excitations were these particle hole excitations of the Fermi surface. And when you zoom in at low energy, there's a scale, Kf, okay, that doesn't decouple from the low energy description. And so when you calculate things like the entropy of, and so this we can relate for non-relativistic theory, Kf, we can relate to the chemical potential, is Kf squared over 2m, the mass of the electron. Yeah, I think that's right. So there's a Kf, or there's an energy scale that doesn't go to zero. It's still present in the low energy theory. Okay, and so, for example, the entropy of a Fermi liquid scales linearly in temperature. It goes like T times mu in 2 plus 1. That's the entropy density. Now, if you had a scale invariant in a CFT, in a scale invariant theory, the entropy density would have to go like T squared. Okay. And so, exactly. So there's a notion. So it turns out that in a Fermi liquid there is a scale invariance. In particular, you can scale as you scale towards the Fermi surface. There is an emergent scale invariance, but it's a scale that doesn't decouple. And this scale can appear in thermodynamic quantities. So the energy, if you calculate the energy density, for example, right, exactly. So the energy density in a CFT, that's now related to T00, right? The VEV of T00 in a CFT in 2 plus 1 would have to go like T cubed. But it won't. I don't want to write down the wrong answer. I forget what it is, but it does not go like that in a Fermi liquid. Okay. So if you want to interpret, exactly. So in a Fermi liquid, all quantities do scale with temperature. They go like temperature to some power, but you will not get these powers from naive dimension analysis, including the naive dimension of T mu nu. Okay, because there's another scale, mu, that doesn't decouple. So a Fermi liquid at the lower scales does have a certain scale invariance, but it's not right. Yeah, T mu nu doesn't have the right dimension of the scale invariance. Okay, so in particular, I'll say it one more time. So if someone said, I give you a scale invariant theory, action that has an action of scaling, you might have said the entropy had to go like t squared, just in a relativistic theory. But that's not true. Okay, that's one manifestation of hyperscaling violation. Okay. Another manifestation that might be more familiar, although is actually phi to the fourth theory. So this is closely related. Okay, this is closely related to what are called dangerously irrelevant operators. But again, it's a scale that doesn't decouple. So for example, if you take phi to the fourth theory above 4 dimensions, the lambda phi to the fourth term is irrelevant. Okay, but if you sit at the critical point, so you tune the mass to 0, and then you fluctuate the mass, you'll need to balance. Okay, so e.g. the lambda phi to the fourth in dimensions bigger than 4. Okay, that's irrelevant. But there are certain quantities that you can calculate at low energies where inverse powers of lambda will appear. For example, if you try to balance the VEV, if you break the symmetry, right, the mass term needs to get balanced by the phi to the fourth term, right, clearly. So for example, if you perturb it with a negative mass, if you want to calculate the response of phi squared, and you perturb it with a negative mass term to balance these, phi, the VEV of phi, is going to have some inverse powers of lambda. Okay? And so there are certain low energy quantities that you calculate where this dimension for coupling will not drop out, right? And so above 4 dimensions, phi to the fourth theory is free. Okay? It's an irrelevant coupling, it doesn't do anything. Okay, so it's certainly a CFT, it's a free, it's a weakly interacting theory. But again, this scaling, this lambda won't drop out of some quantities, right? So that's the sort of thing that happens. It means that there's a scale. Yeah, it's a scale. Hyperscaling violating occurs when there's a UV scale that doesn't drop out of the low energy quantities. An example is a Fermi liquid. The K Fermi, alternatively the chemical potential, appears, for example, in the entropy at low temperature. Okay. If that was helpful, great. If it wasn't helpful, it doesn't matter. So what I mean by hyperscaling violating is just that the metric looks like this, it's a theta in it. Okay? And these certainly come out all the time. Alright, good. So this was meant to, so this discussion and the discussion of Z was just meant that we shouldn't feel too scared by Z and theta. Okay, they're numbers, but they appear in analogous in other contexts. Excellent. All right. Yes?
What do you mean is recording 5 dimensions?
Oh, there's probably some L, there's some like ADS radius or something that I put to 1.
So it's not
no, there will also be, sorry, no, that's right. No, there will be factors of chemical potential in this formula, yeah, for sure. So you can't, actually it's a bit subtle. Yeah, think of it as some factors of the chemical potential, yeah, that's right. Okay, so now what I want to do is probe, actually so okay, we've got our geometry, what can we do with it? Alright, that's the question. So the most fundamental probe in the condensed matter system are the 2-point functions of the currents. Okay, so we'd like to probe these systems. And now remember our setup. All that we're assuming, the name of the game was to take upon a field theory with the U1 symmetry and put it at a finite chemical potential. So if we want to be that general, the only things we're allowed to talk about are currents. Okay, so fundamental probe will be the 2-point function J nu of the conserved currents in the theory. Okay. Now, we've broken Lorentz invariance. So it turns out that without Lorentz invariance, there are two independent components. So to start with, you might think there are three. There's JT, the time component, and then there's what's called JPerp and JParallel, where these are defined with respect to the momentum. Okay, right, so we're going to calculate this as a function of energy and momentum. Okay, and this is a vector, so certainly you can split it into the components parallel to the momentum and perpendicular to the momentum. The conservation law is then omega jt plus k j parallel equals 0, right? That's ddt of that, divergence of that. And so jt and j parallel are related by this. All the information is in two quantities. The density two-point function and the transverse current two-point function. So again, this is called the longitudinal channel. And that's a transverse channel. So again, these are, in our very general classification, these are the only quantities we're only allowed to talk about currents. Okay? I could start counting the two-point functions of fermions or some particular operators. Those will depend on the theory. But all the theories that we're considering always have a current. Right? So these are very general things to think about. And then what, in particular, the two-point function that you care about for these purposes is the retarded Green's function. Okay. Not the Feynman propagator, whatever possibly is more familiar. And so the retarded Green's function of two operators A and B, let me just remind you. So the retarded Green's function of two operators A and B, the function of omega and k, is equal over x and t, Fourier transform, and then theta of t. This is the step function. Okay, so the time integral goes from 0 to infinity. That's why it's a retarded Green's function. You always go forward in time. And then it's the commutator of the two operators. So hopefully most of you have seen that before. So this is the retarded Green's function, and the point about the retarded Green's function is that, of course, it relates the source and the response, right? So if I have some resource, delta phi b of omega for the field, one of the operators b, then the expectation value of a, change in expectation value of a, the function of omega, is the retarded Green's function of a, b. I'm just dropping the k dependence for simplicity. Okay, so retarded Green's function is the thing that relates sources and expectation values, causally. Now, because the retarded Green's function is a Fourier transform, it has i's, so it's important to know that the retarded Green's function has a real part and an imaginary part. And it turns out that everything, the most important, the imaginary part, is the more fundamental quantity. Okay, so let's see about that. So, yeah, it's the most important bit. And let's see why that is. So, suppose you have your system, your sample, your metal, whatever it is, and you take a time-varying source and you apply it. How much work do you have to do to apply this source, right? Or how much heat will you generate when you apply a time-varying source to the system. Okay. So these are very basic things, but it's good to be reminded. So the work done by a time-varying source, periodic source. So you want the average work over a cycle. The rate, sorry, I should say it's the rate that you have to do work on the system to apply this source. So the source is right like it's delta phi here. So you integrate it over a cycle, and so the average over the cycle is this, right? Because the time of the cycle is 1 over 2 pi over omega. Omega is the frequency, dt, the omega dt. Okay, so now there's a bunch of steps, which I'm not going to do, but you can look them up. I think I have the reference somewhere. You can look them up in almost any textbook, but you can also look them up here. Right, and so the answer turns out to be the integral over x and x prime d phi bar, so the complex conjugate of the source. Again, the source is in frequency space. Delta phi bar of x, the imaginary parts of the retarded Green's function, omega x minus x prime, delta phi of x prime. So the main point of this formula is that it's the imaginary part of the Green's function that appears. Okay, so the main point I'm trying, and there's an omega here. Okay, so the main point about this is that frequency times the imaginary part of the retarded Green's function, and that frequency measures how much work you have to do. Well, which is actually the same, which is how much heat you generate. When you apply the source. Okay, and so the reason that that's pretty useful, right, is that this basically, right, so very good. So let's say you've got what would be the simplest case of this? Yeah, so let's say you had a harmonic oscillator, not damped, perfect frequency, that's on frequency. This thing is a delta function at the frequency of the harmonic oscillator and 0 everywhere else. Okay, so you have to drive it at exactly the right frequency to do work, otherwise you don't do any. So just to repeat that. So another way of saying this is that this quantity, let's just forget that. It measures the number of excitations in the system with energy E, or energy omega. So again, for example, suppose you've got some quantum mechanical system with a bunch of energy levels. Okay. Then the imaginary part of the retarded Green's function of the system is basically the sum over delta functions of all differences in energy levels. Okay. Right? So the only way, right, you've got a quantum mechanical system with a bunch of energy levels, the excitations of the system are when you jump something from one energy level to another one. Right? Those are the excitations that you have. And what this the imaginary Green's function, the imaginary part of the totally Green's function is basically the sum of all possible energies that you can excite the system at. And that's why it also shows up. That's how much work you have to do. If you don't excite anything, you don't do any work, nothing happens. Right? Okay. So, this is a very nice quantity because if you know this, then you know what the system is made up of, right? You know what excitations there are in the system. Okay. So, it's a very nice quantity. So before we calculate this for the black holes, right, because we're trying to understand what, so the black holes have this geometry, but what can we learn about what it looks like, what it's made of? Okay. So as an example of this, let's do the Fermi liquid case. All right. So an example. Let's do free fermions. By the way, just for people to think more in terms of amplitudes, this is obvious, right? So, you know, imagine a free theory. Well, we're about to do this. But the Green's function, the two-point function of, well, actually, even better. Two-point function is just something like this. And the imaginary part of that, you know, the propagator is 1 over p squared omega squared minus m squared, right? That would be the propagator. The imaginary part of that is just the delta function at the mass. Okay, that's all that's happening. Okay, so let's calculate the imaginary part of the two-point function for the density operator for free fermions at finite density. So free fermions at T equals 0 and non-zero chemical potential. Okay. So the charge operator is psi dagger psi. Okay. That counts the number of electrons. And so if you want to calculate the two-point function of this operator, it's clear that this is just this diagram. You have a JT, each one has 2 fermions in it, so we're going to get 2 lines that do that. And so the fermion propagator, right, is something, so the fermion propagator is something like schematically 1 over omega plus BF, K minus KF or something. Actually, we can even do it, well, yeah, something like that. And so it's trivial to do this loop, okay? And it's even easier to take the imaginary part, right? Because as you know from, what's it called, unitarity, the optical theorem, right? The imaginary part of this diagram, you just cut it and you sum up all the on-shell states, okay? That's all we're calculating here, okay? And so what you find, so it's easy calculation that you can find in the appendix of this paper. We get the following plot. Find that the imaginary part of the retarded Green's function of the currents. Okay, so that divided by omega, limit as omega goes to 0. So let's look at the lowest energy excitations of the system. It turns out that the imaginary part of retarded Green's functions are odd. Okay, so to get a finite number, you divide it by omega. So this is the low energy limit of this retarded Green's function as a function of k. All right, let's see what that looks like and make a plot. Okay, so I'm saying you calculate this diagram, then you take omega to 0, and I plot it as a function of momentum. Okay? and this is meant to be a measure of how many excitations there are. This will be measuring how many low excitations there are in the system as a function of k. And so what you get is a plot in two, if you do it in 2 + 1 dimensions, you get a plot that looks like this. That drops to 0 at the point at 2kF. Okay. So let's understand. This is very easy to understand. Also very nice. So let's see what's happening. Okay, so again, according to what I was saying before, this is a measure of how many excitations, low energy excitations there are as a function of momentum. And the claim is there are none above twice the Fermi momentum. So let's draw a picture. So that's momentum space. So what are the excitations? So this is a charge-charge 2-point function. So what that means is that we take a charge and we move it by an amount k. Right? That's what this k means. So let's take an excitation here, some charge, and let's try to move it by some amount k. So for example, we could move it, right, very good. But we want to not cost any, we want to move it without it costing any energy, right? Because we've taken the low energy limit. So where can we put it? Well, the whole Fermi surface, or where all the low energy excitations live on the Fermi surface, right? So we can take this charge and we can move it here, for example. That would be k, and that costs no energy, right? Because all the fermions on the Fermi surface are 0 energy. Or we could take it here, and that would cost no energy. Or we could put it there, or we could put it there. Okay? But if we took this fermion and put it over here, that would cost energy because we're away from the Fermi surface, right? Remember the zero locus, this k minus kf tells you that 0 energy excitations are on the Fermi surface. So the furthest we can go in momentum space is the diameter of the Fermi surface, which is exactly, of course, 2kf, right? Kf is the radius. We're imagining it's a sphere for simplicity. Okay? So it's clear in this picture that low energy on shell excitations will have k, necessarily have k less than 2kf. Okay. So this is a very distinctive property. By the way, look, if you have, let's say you had a, okay, sorry. So this is a very distinctive property of a Fermi surface, right? That the low energy excitations are smeared in momentum space, okay? But they're not arbitrarily smeared. They stop at 2kf. Of course, to get this precise curve, you need to do the calculation, right? But, okay. That's the idea. So let's contrast this. What if you do this for a relativistic boson, right? So the boson, boson or fermion at 0 density, so no charge. Well, there, the only low energy excitations live at the origin of momentum space, K. All the low energy excitations there. So if you start with the non-shell charge here, and you move it there, somewhere else in momentum space, that's going to cost you energy, because for these guys, the energy just goes like K. I'd say it's relativistic. Right? It doesn't go like K minus Kf, it goes like K. So if you give a particle any momentum, it'll cost you energy, and you won't be able to do that. Right? So the imaginary part of the retarded Green's function at 0 density is basically going to be a delta function at omega squared minus k squared. So in particular, if you put omega to 0 first, then it's 0 at any non-zero k, right? You can't, they know in a relativistic theory, kinetic energy costs energy, so if you have momentum, you necessarily have energy. Now what if you heat it up? It's also So now let's take just a final example. Let's imagine taking this boson and fermion, or fermion at zero density and heating it up. Then you will produce some degrees of freedom here. Okay, so you have a thermal distribution of states, right? But it'll be Boltzmann. So at finite t, you have some Boltzmann excitations. Okay, and so what you find is that the imaginary part of the retarded Green's function omega k of omega, limit as omega goes to 0, so the zero energy excitations, it will go like e to the minus the energy divided by the temperature, which is k in this case, right? Because, so assuming they have a dispersion relation, omega goes like k, right? So, again, so at finite temperature, your excitations want to be there, but there's a small probability that you'll create spontaneous excitation here, right? And so, remember, well, if you remember in Fermi's golden rule for the rate of scattering, it depends on the density of states that you're scattering into, right? So when you heat it up, there's some exponentially small density of states exciting here, okay? And so you can move into those states, right? And that's this. So this is very different, okay? So fermions at finite density have low energy excitations at finite momentum. But if you didn't have a density, the low energy excitations at finite momentum are exponentially suppressed at low temperatures, okay? So that's all very physical and very reasonable, right? What I'm trying to illustrate at the moment is that this imaginary part of the retarded Green's function is a very nice quantity. When you calculate it, you immediately get a picture of what's happening. Oh yeah, one last thing. This is pretty cool too. So, I haven't mentioned the word Pauli exclusion. I didn't put it in anywhere. So suppose you didn't know about Pauli exclusion. But if you calculate this diagram, you'll see this result, and you'll see that the low energy excitations are getting pushed out to finite momentum. How can that possibly happen, right? Because normally kinetic energy costs energy, right? There shouldn't be low energy excitations with finite momentum. The reason there are for fermions is because of Pauli exclusion, right? So this two-point function knows about Pauli exclusion. Good. Any questions about that? Okay, so now that we know what happens in conventional matter, now we can say, well, let's have a look at these black holes, let's calculate this two-point function, and let's see what they look like. And then we should be able to get a direct sense whether they have a Fermi surface or not. Okay? And the reason this is, again, the reason this is really nice is that a Fermi surface was defined with, we started off by defining a Fermi surface with fermions, right? It's like one fermion, two fermions, three fermions, building up the Fermi surface. That's an intrinsically weakly coupled description, okay? But here we just calculated the density two-point function. That's well defined at any coupling, okay? And so this is a very nice diagnostic of a Fermi surface. It shows you that the degrees of freedom are spread out in momentum space without ever talking about single particle states. Right. So next up, let's calculate. So what I want to tell you is how to calculate the retarded Green's function for black holes. So I'm going to be a little brief, but if people, there's some slightly more extended discussion here. So, and for simplicity, let me do the scalar field. Okay, so suppose we have our bulk. We have some operator O that lives on the boundary, and we want to calculate its two-point function. Okay, that operator is dual to some scalar field phi in the bulk, and right, we'd like to calculate this. In particular, I'd like to calculate the retarded Green's function. It's a function of omega and k. So probably many of you have seen calculations of Green's function. You know, they're certainly in the original papers on ADS-CFT and so on. But for these kind of applications, there's sort of a slightly different way of setting up the calculation, and so I want to show you. That. Okay. So first, we're always going to be in the planar foliation. So this is r. That's the r coordinate. That would be t and x for the boundary directions. So clearly, right, I told you the fundamental dictionary, right? Right, so the Cartesian functions of bulk with phi going to some source was the expectation value of this thing in the boundary. Okay. So to evaluate this, the first thing I will need to solve the equation of motion for the scalar field. Let's say it's like that in the bulk. So the idea is we're going to solve this equation subject to some boundary conditions that phi goes to phi 0, and then that will give us a generating function, and of course we calculate the two-point function by differentiating twice the generating function. Okay, so what you want to do here is firstly, certainly we want to do a Fourier decomposition, so phi will be phi of r, e to the minus I omega t plus ikx. When you do that, if you plug that into here, you'll get some second order equation, differential equation for phi, for this guy. So you'll get something of the form phi prime prime plus some function of r omega and k phi prime plus another function of r omega and k times phi equals 0. Schematically, right? I mean, well, it is of this form. So indeed, a lot of effort in applied holography goes into trying to solving these silly linear second order equations. But okay, so that's what you have to solve, right? You've got some background, you write down the Laplacian on this background, you Fourier decompose it, and you're left with some second order equation, ODE, right? It's a second order linear ODE. It's not that scary, but okay, one has to solve it. So, you need to solve. But what I want to tell you about in the next few minutes is that, you know, before just sticking this onto Mathematica, which is, you know, numerically certainly is very easy to do, it's worth stopping and thinking a little bit about what we actually want to calculate. Okay. Okay, so first thing we can do is we want to solve this equation near the boundary. So it goes to 0 in my language. And you'll find that there are two, as I'm sure many of you know, there are two independent solutions. One will go like, let's be in 2 plus 1 dimensions. You'll get r to the 3 minus delta, some constant, some leading terms, plus r to the delta times another constant, where delta is the scaling dimension that depends on the mass of the scalar field. Oh, indeed. And so this we fix. That's our boundary conditions. Okay, we fix phi 0. That's what we want to fix. And it turns out that, actually, I don't think I said this before, but I probably should have. I think I did actually, right. That this guy, sorry, phi 1, that's the source, and that phi1 is always the vev. That's the expectation value of the operator. I think I said that before in the context of this was the chemical potential, that was the expectation value of the charge. Okay, so universal thing, but the first constant is the expectation value, sorry, is the source, is the coupling, and the second constant is the vev. Okay, so it's a universal thing that you can differentiate when you differentiate the vev is what you get when you differentiate this once, you bring down an O. Okay, that vev turns out to always be the second term. Yeah, everybody said that. I'll say it once more. This is really Hamilton-Jacobi. I don't know about you, but whenever you first learn classical mechanics and someone starts talking about Hamilton-Jacobi theory, it seems like the most useless thing in the world that you're never going to use for anything. But in holography, it's really the right way of thinking about all of this stuff, right? Because everything you're evaluating the actions is a function of the boundary data, right? That's exactly what Hamilton-Jacobi theory is. Okay, so the right language. So if you haven't thought about Hamilton-Jacobi since you were, an undergrad, this is the right time to remind yourself. Okay, it's very useful. Good. Okay. So, but now remember that the retarded Green's function is just a ratio. So remember that the retarded Green's function, the vev, is the retarded Green's function times the source. So that means that the retarded Green's function is just, again, I'm dropping constants of proportionality, all the one numbers. The Green's function will be phi1 divided by phi0. Okay. Right. So to calculate the retarded Green's function of O, all we need to do is fix the so-called non-normalizable mode, this guy, solve this equation, subject to another boundary condition that we're about to tell you, and that other boundary condition will fix phi1 in terms of phi0. You then take the ratio, and that's your Green's function. Okay. So I mentioned another boundary condition. So there are two constants, so if you want to fix both of them, you need two boundary conditions. So then what we have to do is solve the equation near the horizon, which in the coordinates I'm using is r goes to infinity. Okay. And there you'll find two solutions. Phi will go like phi infalling e to the I omega r plus phi, I guess, outfalling, e to the minus I omega r. Those will be the two leading behaviors near the horizon. Okay, basically, something can come into the black hole, or it can come out, but as you know, it shouldn't come out, and so we have to set that one to 0. Okay. So it turns out that regularity at the horizon requires infalling boundary conditions. So we have to set that to 0. So there's a lot of confusion. So this is really just like, so the problem you're left with is exactly a quantum mechanics problem. So it's a textbook quantum mechanics scattering problem. So of course, not for a potential as you'll find in the textbook, but the setup is, so we imagine we have R, the radial coordinate, it goes from 0 towards infinity. Okay. We've got some second order equation, which by the way, obviously you can always get rid of phi prime, right, by putting it into a sturm Liouville form, right? So this is of the form of a Schrödinger equation for some potential. We know that the modes are growing and decaying at infinity, so actually, roughly you're going to find something like this. The potential decay, it can do whatever it wants to do, and then it grows at infinity. Well, let's see. And so here, you know what? Let me go over here. again. So what you end up solving is a quantum mechanics problem with some potential. This is r equals 0, r equals infinity, so this is the horizon. This is the boundary of ADS. And it turns out the potentials you get look something like this. Okay, so remember, ADS is like a box, right? It wants to always reflect things in. So here, there'll be a mode that goes like that, and a solution that goes like that, okay? Because it's just, there's no potential. And here, there's a decaying and a growing mode. They're not exponential in this R coordinate, they're power law, but that doesn't matter. Okay, and so the name of the game is that you say nothing comes from the black hole, so you set that to 0. And so given the ingoing boundary conditions, you then want to take, this is phi 0, this one is phi 1, right? So you set up your Schrodinger problem, impose waves only going that way, and then the Green's function is the ratio of these two. Okay. So if we give an energy, if we give an omega, so then your equation, right? So the overall constant doesn't matter. Set the overall constant to 1, impose that way, and then take the ratio of these, and that's the Green's function. This just turn off. So yes, it did. I didn't do anything. Hello? Yeah. Excellent. So, right? Okay, yeah, exactly. So, the Green's function of omega is now this ratio. Okay. Oh, good. Lots of time. So now, what will happen? So far, so good. Now, what will happen though, when you land with this potential, of course, it is not going to be one that you ever saw in a quantum mechanics book, and if you give it to Mathematica, it won't solve it. Okay, so you're going to end up with some, most of the time, unless your black hole is something like BTZ in 3 dimensions, then the solution is in hypergeometric functions. Most of the time, you can't solve these equations. All right. So here's the first step that you do. So. Right, so clearly, the shape of this potential depends on the background, on the black hole. Right, there's some space-time, there's some equation of motion. You perturb it, you get this. Now, I think life forgets what we really care about are the low energy excitations. Okay, those are the universal. I don't care. We know what n equals 4 is, or whatever it is in the UV. That's not the objective, right? The objective is to understand the low energy excitation, the emergent low energy excitations of this phase of matter that we've created. So we care about omega goes to 0. Okay, so let's try to simplify life. The equation is going to simplify a lot at small frequencies. So your first inclination might be, well, okay, I just put omega equals 0 in the equation, and that should work. Well, that clearly won't work for 2 reasons. One is that, okay, I guess I erase it. I told you that the imaginary part of the Green's function is odd in omega. Okay. So if you just set omega to 0, you're going to lose the imaginary part. So you need to keep some omega dependence if you want to get a hope of getting the imaginary part. And secondly, what we see here, this is the near horizon behavior. The near horizon behavior was like this. This was R goes to infinity, okay? But it's clear then that omega goes to 0 and R goes to infinity will not commute. Right? So if I set omega equals 0 and then solve the equation at large R, I clearly won't get that because there's no omega anymore. Okay? So it turns out that you can't just put omega equals 0 because omega goes to 0 and R goes to infinity. That's the near horizon limit, don't commute. Then you do something that's beloved to astrophysicists and many string theorists and all kinds of physicists. So you have to do a matching. There's a matching problem. Okay. So, which I'll just outline. So what's the problem? So let's draw this line again. This is r equals 0. So r goes to infinity. And we'd like to extract the low, so let's call this 1. Okay, that's the chemical potential. It's some scale in the background. Okay, let's say it's the chemical potential. And then there's another scale, let's put it here, which is 1 over omega. Because omega is very small. Right? Omega is going to 0. So, and so the problem was that there are omega r terms in the equation. And so whenever these terms are important, you can't set omega to 0. Okay? So there'll be terms in the equation that will be like 1 plus omega, schematically like this. And so this is the example, right? That if you set omega to 0, you just drop that term. But for any finite omega, if r is sufficiently large, then this term is more important, right? The limits don't commute. Right? So, however, where you can drop this term, you can drop when omega r is much, much less than 1, right? Which means that r is much, much less than 1 over omega, right? So that's here. So over this whole region, you can set omega equals 0. Safely in the equation. And you can solve the equation with omega equals 0. But then you can take another region, this region here. This is r much, much less than 1. Okay, right, that's 1. Again, 1 is like, it's the characteristic scale, right? So roughly, one more time. That was our space-time, where we had some flux. There's some scale here, which is r of order mu, which is what I'm calling 1. And so r, much bigger than 1. That's the near horizon. That's the near horizon region here. Okay? So this is the near horizon region. Okay, so, and then the beauty of it is that when omega is much less than 1, there's a regime where these overlap, a parametrically large regime, right, which is so for omega very small, then for r much bigger than 1, and much less than 1 over omega is an overlap, parametrically large overlap regime. Okay, so it's important to understand when you're doing this matching stuff, is that you need to have a parametrically large region. Okay, it's not enough to have r between 1 and 2 that overlaps. Okay, you need to have a scaling regime. You need to have a regime where you have an arbitrarily good overlap. Okay, so it's really important. This is a parametrically large region. So by the way, just to be clear, okay, this is I know from experience, it's a very common mistake. You can't just say, I'm going to have one equation for r less than 1, r much less than 1, and r much bigger than 1, for example, and then I solve it and I match them. I match the value of the function as derivative at r equals 1. Okay, that is absolutely not allowed, right? You have to have, may sound obvious, but yeah. So you need to have a big parametrically large window where your two expansions are both valid at once. Okay, that's how you match. So that's not allowed. Okay. So you need a parametrically large window. Okay. Now, but this is now interesting because we see that the only place where you care about all the frequency dependence it's going to come from this near horizon region, okay, at low frequencies. And everything, the rest of the space-time, has no omega dependence. It's basically just going to be a constant in terms of omega. It's not, it won't do anything. How much? Like 1 minute? Oh, okay. I think there's some time dilation going on with this clock. All right. Let's read 2 minutes. Okay, so it turns out now, I won't go through it. So remember, that was the name of the game. You impose your ingoing boundary conditions here, and you want phi 0 over phi 1 here, right? That's what we want to calculate. So it turns out if you do this matching, it's like a 10-minute exercise, it's a short exercise. But if you do the matching, you find that the imaginary part of the retarded Green's function at omega, right, the guy out here, is proportional to, so there's some number here that does not depend on omega, it's just a number, times what we can call the infrared retarded Green's function. And so this is some quantity that you can calculate purely from the infrared geometry. Okay, so when you solve the equation in near horizon geometry, yeah, right. So what will happen? Yeah, let me. Okay, so this is purely from the near horizon geometry. So what is this guy? So what this is, so again, remember we had our Schrodinger equation. There'll be some stuff that look like the potential will look something like this. And then, so here we impose outgoing. Here there's a growing mode and a decaying mode. Right? What basically happens is that the matching is like here or something. Well, actually more like here. And near the boundary of the IR, so sort of over here, there's also a decaying and a growing mode. Okay. And so this retarded Green's function in the IR is basically the ratio of these two modes. Okay. So another way of saying it, in this, when you solve the wave equation in this overlapping regime, where this is the ultra simplified regime, right? You take R large and you set omega to 0. Okay, here. You'll find the solution is typically these two powers, and it's the ratio of the coefficients. Okay, and then what this matching will show you is that this ratio, so let's call this phi 0, phi 1, and let's call this phi 0 IR and phi 1 IR. This retarded Green's function is the ratio of these two guys. And so going from this ratio to that ratio, nothing interesting happens. It just gets multiplied by a constant. Okay, that's what I'm saying. Okay, we'll pick up on this afternoon, but let me just repeat the main point. That to get the retarded Green's function, which is the ratio of two things at the boundary, at low frequency, up to a constant, you can get everything just by solving the near horizon equations. Okay, and this fits with the intuition of ADS-CFT that the near horizon is the low energy region. Okay. So the near horizon knows everything about how many excitations. By the way, this matching doesn't work for the real part, okay? So the imaginary part is the physical thing. It's counting how many excitations. This thing is saying how many excitations at low energy are there in the system, okay? And what this matching is telling you is that that question only depends on the near horizon geometry. Okay, so that's a huge simplification, because the black hole solution is some horrible, complicated thing. But the near horizon geometry has this nice scaling form. Okay, so we only need to use that.